So the ratio of lateral to linear strain is called Poisson's ratio, that is mu. You have already read this things. Then shear stress and shear strength are related by the this relationship tau is equal to Gy. G the shear modulus or elastic modulus in shear stress. So you know what is that. Tau is the shear stress and gamma is the shear strain. Tau is the shear stress and gamma is the shear strain. G is the constant. Or we can say this, we can call it that shear modulus or elastic modulus in shear stress. Then another term, that is bulk modulus or volumetric modulus of elasticity. That is defined as the ratio between the mean stress to the volumetric strain. Please remember this bulk modulus, because it will going to be used for the derivations, different derivations in this topic here. And the large use of this bulk modulus, the bulk modulus is the volumetric modulus of elasticity. Is the defined as the ratio between mean stress. Please remember this term, mean stress. This is not the stress. This is the mean stress to the volumetric strain. The K is equal to sigma m. M for mean stress, sigma m by del. Okay. So all moduli are related through the Poisson's ratio. That the relationship between these constants, elastic constants. This is the elastic constant, not the plastic constants. So this is the relationship between the elastic constants. G is equal to, or we can say E is equal to 2G into 1 plus nu. K is equal to, E is equal to 3K into 1 minus 2 mu. This is the relationship all moduli related to Poisson's ratio, through Poisson's ratio only. There are the other relationships also. So we comes to the plastic deformation. Following the elastic deformation, material undergoes plastic deformation. After the elastic deformation completed, then there will be the plastic deformations. Also characterized by relations between stress and strain at the constant strain rate and temperature. So it will be characterized by the relation between stress and strain at constant strain rate and temperature. At constant strain rate and temperature. The main characteristics characterization by the plastic deformations. Then microscopically it involves breaking atomic bonds. So that means the plastic deformation means we are going to talking about the permanent shape change. So how it will be permanent shape change? If the atomic levels will not be break, so there will not be possibilities of the plastic deformation. That's why in plastic deformation, the breaking of atomic bonds, moving of atoms, then restoration of bonds. After that, when we are going for the shape change, no? So we are going for the permanent shape change. So we need to break the atoms first. The bonding between the atoms should be break first. After the breaking of the bonding between the atoms, then the atoms, the movement of the atoms will be started to the new positions. Okay, then at a stable condition, then again the bonds between atoms will be started and the material will be, the shape of the material will be stable. So that's why the plastic deformation is happens. So this is microscopically. If you see it microscopically, this is the process: breaking of atomic bonds, moving of atoms, then installation of again the bonds. So stress strain relationship here is complex because of atomic plane movement. Always, as we read in your, that is called Introduction to Physical Metallurgy, IPMEF. There is a slip and dislocations, slip and twinning is there. It is very complex method because of atomic plane movement. The atom planes will move there. Atomic plane movement, dislocation movement, and the obstacles they encounter. Okay. The crystalline solid deformed by process, slip, and twinning. As we have said, studied these things in our physical metallurgy subject. The crystalline solids deformed by slip and twinning. That we are talking about the metals. All metals are crystalline metals. So it will be deformed by the process of slip and twinning. The amorphous solids deformed by viscous flow mechanism without any directionality. There is no directionality for the amorphous solids. So they will deform by viscous flow mechanism without any directionality. Please remember these 2 points because it will be asked in like competitive exams. The questions will be asked in competitive exams like that. So if you see here, the because of the complexity involved, theory of plasticity neglects the following effect. In theory of plasticity, some effects we have to going to be neglected because of the complexity in calculations during the calculations. So what is that effects we are going to be neglected here? Going to be omit here. That is the unelastic strain. Will not considering the unelastic strain, which is time dependent recoverable strain. It is a time dependent and a recoverable strain. So there is no recoverable strain in plastical deformation, and we are not going to be considered this unelastic strain. So then hysteresis behavior. Hysteresis behavior means resulting from loading and unloading of material. We are not considering the hysteresis behavior also. Then the Wassinger's effect. What is that Wassinger's effect? Wassinger's effect is nothing but the dependence of yield stress on loading path and direction. The dependence of yield stress on loading path and direction. So that is Wassinger's effect. These three things we are going to be neglected, or we have to not to considering during the plastic deformation of the metals. So if you see show you that Wassinger's effect. So one thing I have to show you. What is that Wassinger's effect? Need to go for the another share. Visible screen. My screen is visible now.
Yes, sir.
Okay. See this. This axis is stress. Sorry, this is our strain. Strain. This is stress. Okay. So if a material is loaded within the elastic limit, so a ductile material, if you consider ductile material, this will be the plot. This will be the plot. If a material is loaded within the elastic limit, this is the case. If at that instant we will remove the load from the body. If at that instant we will remove the load from the body, then what happens to the material? So that the way the deformation, this is the line, this is the station line, the way the material will deform, the buyback, when we are saying the elastic deformation, that means the material will regain its original shape and sign. How it will be regain its original shape and sign? How it will be regain its original shape and sign? So this is not the way on which the material will back to its original positions. So when you remove the load, the material will bring back to the original position like that, in that way. Again, see that the material started from this position. This is the position. Material started from this position, but it will be during the recovery process. It will be in this position. Okay. So what happens if you again reloading the material, if you again reloading the material at this point, if we are reloading means that is the we are in this case we are loading the material in tensile stress. This is tensile stress. This is here it is tensile stress. When at this point, if you are applying at this point, if at this point we are applying at this point, if we are applying again applying the compressive stress, the diagram will be like that. The stress strain diagram will be like that, in that manner. Okay. So again, if you removing the load from here, again if you removing the load from here, the stress strain diagram will be changes like. It will not regain its. It will not. The metal will not recover at this position. It will be recovered somewhere in these positions. So this curve is known as the hysteresis curve. The loading and unloading directionality. The loading and unloading directionality is called the hysteresis curve, and this is the Bosinger's effect. If you see the where we have left there, removing this. Okay, see this. Bosinger's effect. What is that Bosinger's effect? Dependence of yield stress. The dependence of yield stress on loading path and direction. The dependence of yield stress on loading path and direction is called Bosinger's effect. There we are going for the what is sorry, this is removed. Okay. Visible? Screen is visible though?
Sir. Yes, sir.
So please remember these things. What is Bosinger's effect? Somewhere the questions will be asked for the short questions. You will draw it with the diagram. Okay. Dependence of yield stress. How the yield stress will be changed from during the loading path of the loading path and directions. Different loading paths. When we are changing the path from tensile to compression, how the path will be changes and what will be the direction. So that is your Bosinger's effect. Next, the equation relating to stress and strain are called constitutive equations. We will read that in the consecutive classes. The equations relating stress and strain are called constitutive equations. Rather than in plastic deformation, so you have the equations of the constants. We have the equations of the constants. That is, we have there is no relationship. There is no equations like that. But here it is the constitutive equations. Then true stress strain curve is called flow curve, as it gives the stress required to cause the material to flow plastically to certain strain. This is the important point. You have the question of the you may have the question of the what is that flow curve. Flow curve is nothing but the true stress strain curve. That is called as the flow curve. True stress strain curve is called as the flow curve. Why it is flow curve? Flow means which is flowing. Where in plastic deformation, what is flowing? The material's deformation is flowing or going on. So that's why it is called as the flow curve. Okay. And then because of the complexity involved, there we have been stress strain relationship imposed here. What is that? Sigma is the function of epsilon dot temperature or microstructure. Okay. Epsilon dot is a strain hardening. Okay. Rate of strain. T is the temperature and microstructure. Strain, rate of strain, temperature and microstructure. So there is a relationship sigma is equals to k e to the power epsilon to the power n. This is the called as the flow curve equation. This equation is called as the flow curve equation. That is also called as a strain. That n is called as a strain hardening exponent, and it is varied from 0.1 to 0.5 according to the materials. N is varies from 0.1 to 0.5. This is the flow curve equation. This equation, this is the very important equation. Sigma is equals to K epsilon to the power N. Okay. And then sigma is equals to K epsilon dot to the power M. So M is the strain rate sensitivity. Epsilon dot is the strain rate and M is the strain rate sensitivity, that is from 0.4 to 0.9. Then see another relationship, K is equal to epsilon 0 plus epsilon to the power N. N is the strain from previous work. Epsilon 0 is the strain from previous work. N is the same, the strain hardening exponent. N is the same, the strain hardening exponent, but here the epsilon 0 is the strain from the previous work. That means before you go for the final deformation, what will be the deformation in the material previously. Then another relationship, that is called as sigma is equal to sigma 0 plus K epsilon to the power N. Here sigma 0 is nothing but the yield strength. Sigma 0 is nothing but the yield strength. These are the important relationship which is going to be used in our calculations. So if you see the tensile stress strain curve here, the engineering stress strain, this is the I'll show you three diagrams. Three diagrams here. First one is the engineering stress strain diagram. Second one is the true stress strain diagram, and true stress strain diagram corrected for knocking. See, this is for the stress strain diagram for the ductile material. This one, this one. See this one. Okay, Balaram. Don't do any annotations. Repeatedly, I am saying this is second time in second class. Okay, rather you leave. If you have any issues, so rather you leave. See this. This is
Sorry,
the
sir.
stress strain diagram. This is the true stress strain diagram. The line I have drawn here. So sorry, sir. This is the engineering stress strain diagram for a ductile material. Engineering stress strain diagram for a ductile material. So as you know that there will be there are several points: the proportional limit, the elastic yield point, then the ultimate stress point, then we have the fracture necking, then after that fracture. This is the maximum load point. This is the maximum load point, or we can say this is the ultimate stress point. After that, the metal will going for the necking. If the metal is ductile, then it will be necking. Then after that, there will be fracture. So this is the true engineering stress strain diagram. But in case of in engineering stress strain diagram, what happens? We are taking the original dimension, original area in throughout the calculations. In original area, if you are writing this, the original area A0 in engineering stress, in calculating the stress, we are using F by A0, the original area everywhere. But in case actually what happens during the deformations, during the plastic deformations, Anubha, Anurva. So during the plastic deformations, what happens? The area of the material, area of the metal always changes. That always changes. That is always true for the any type of deformations. So if you are considering the original area, or we are considering the instantaneous area means the area at that particular point. That means that will give us something different, that is called as true stress. If you are writing this sigma t, so the equation changes is A by A. Simply A. What is that A? A is the instantaneous area, particular area. So if you changing this, rather the diagram, if you are saying here, the actual the true stress diagram from the maximum stress, it will be flowing in stress diagram. That will be in that manner. The stress diagram. After the achieving the maximum load point, ultimate stress point here, the ultimate stress point, the necking form, and then the Stress level decreases here. This is stress, na? This is stress. This is strain. The stress level decreases. But in case of if you're going to the if you're going to the true stress strain diagram, if you're using the instantaneous area, means area continuously decreases. Here area continuously decreases. If area continuously decreases, then stress will be increases. See this point. If area continuously decreases, the we are going for the deformations. Sorry for the interruption. The network issues are there. So we'll continue here. We left. See, we are showing the stress strain diagram. The stress strain diagram is here, like just rotating. This is the engineering stress. There is sigma. This is strain. As I said, this true stress strain diagram sigma T is equal A by area. A by instantaneous area. That means during the plastic deformation, the area is continuously decreasing. If the area is continuously decreasing, then stress will be continuously increasing. True stress will be continuously increasing. So rather, this type of diagram, the stress will never decreases. The stress will be going further this way. So this is true stress strain diagram. This is true, and that is engineering. This is the engineering. The engineering. Because of this, the area increases, area decreases means stress always increases. So stress will, there is no chance of decreasing the stress. This portion will not be there. The stress is always increases. So this will be the graph. So same thing will be shown here. See this. Same thing will be shown here. The purple graph, this graph. This purple graph. See this. After the achieving maximum ultimate stress point, tensile stress point, the stress will be increasing, going on increasing. There is no decrease in stress levels. There is no decrease in stress levels. And this green curve is for so that if there is a necking, then this curve will be like that. The curve will be going to be like that. This is the true stress strain diagram. This is true. Both are true. Sorry. This is true stress strain diagram, and this side is engineering stress strain diagram. Engineering stress strain diagram. Okay. So I think this is all about your true stress and engineering stress strain diagram. You have to correct this. You have to correct the stress strain diagram. You have to draw the stress strain diagram, the true stress strain diagram. Okay. So we'll move next the section. This is the continuum tensile stress strain curve. So this the engineering stress strain, and this the purple line is see the figure and see this. This purple line is the true stress strain diagram, and this blue line is Hooke's law. This blue line, this is the blue line. Just annotating. If you are not understanding what is the notations or the lines, please ask. Okay. So this blue line represents Hooke's law. This blue line represents Hooke's law. So this red line, Hooke's law at 0.2% offset strain. This line. What is the use of this Hooke's law at 0.2% offset strain? Can you tell me? Can you tell me what is that Hooke's law at 0.02% offset strain? See, this is the blue line. This is the blue line. This is the Hooke's law. Hooke's law means what? The stress is directly proportional to strain. This is the line, the proportional line. Stress strain proportional. This is the Hooke's law line. So we will draw a line parallel to this line. Parallel to this blue line, we are going to draw a line. That line will be at the 0.2% offset of strain. This is the strain, total strain. With the offset of 0.02. From here we will going to the calculate the 0.2 percentage of this total strain. Then we will draw a line parallel to this Hooke's law line, blue line. So this is the line where this line will intercept. This is the intercepting point. This intercepting point represents the yield stress of the material. This intercepting point represents the yield stress of the material. This is the way in which we are calculating the yield stress from the stress strain diagram. This is the method. If you are in future, if you are going to do some research work, then you remember these things. This is the method how to calculate the stress strain curve, how to calculate the yield point. So these are different points are given here. Sorry. A is the starting point. See this. A is the starting point. B the proportional limit. C the elastic limit. This point. C the elastic limit, and D is the yield limit. See this. Where the rail line intercepts, the offset line intercepts. That is the yield point. So G is the 0.2 percentage offset strain. This is G, and H is the yield strain. This is the yield strain. So this is the way how can you calculate the yield stress and yield strain. If you are connecting this point here, if you are connecting this point here now, you are calculating the yield stress. That is sigma y, and if you are see the perpendicular line H, then it will the yield stress. Sorry, yield strain. This point is the yield strain. So we'll move next. So apart from different strengths and strength points, two other important parameters can be deducted from the curve are the resilience and the toughness. I think we both, you both are aware about, you are all aware about these two terms, the resilience and toughness. Resilience, the ability to absorb energy under elastic deformation. So I'll show you here. If this is the stress strain diagram, this is the elastic limit point, the area under the curve, this is sigma, this is epsilon. Ability to absorb energy under elastic deformation. This is, if this is the complete stress strain diagram, and this is the elastic limit point. So energy under this elastic limit point is called resilience. So it is resilience. Okay. Then what is the toughness? The ability to absorb energy under loading involving plastic deformations. That is toughness. So if you are going for the plastic deformations, again I am drawing here plastic deformations. So this is this total area under the stress strain diagram, including the plastic and the elastic deformation is toughness. Yes, that is toughness. Okay. You should clear about two terms. These two terms. What is resilience and what is toughness? So there are the represent combination of both strength and ductility. Toughness represents the both strength and ductility of the material. So here the if resilience is represented as UR, resilience is represented as UR. So that is UR is equal to half of S0 E0 into equals to, or maybe that is half of S0, that is the initial stress, S0 that is written as the initial stress, E is the strain, and here it is the E is the Young's modulus, so S0 by, or we can say half A square by E, 1 by 2 E A square. That is the area under the curve, or you can say the resilience. Then there must be the toughness. There is toughness. So what is the toughness? Toughness is area under this curve total, including the elastic and plastic deformations. That is SU equal EF. Then maybe equals to S0 plus SU by 2 into EF. So it will be for brittle material. It is this relationship for the ductile material. This relationship, this for ductile material, and this is for the toughness for the brittle material. 2/3 of SU and EF. SU means the ultimate stress, and EF is the final strain. Okay. Yeah. So we'll go next then. I think I will not related this topic now. Then the yield criteria. The yield criteria must be in your course. We'll go through this the yield criteria. Yield criteria we need to calculate this J2. So J2 is a invariant stress deviator. What is the invariant stress deviator? What is the three-dimensional stresses? So we'll go through the details of this details. Then we'll go for the yield criteria. So this is the problematic. I from the very starting I'll clear you that it is a problematic chapter. There is the either questions come as the problems or the derivations. A short question that are the short questions like you ask what is Bush-Jones effect, inelastic condition. That may be some questions, short questions. That all the short questions may be related to your some derivations or problems. So this is a 100% derivation or a problematic topic. So you prepare accordingly. Don't miss where you find any difficulty. You can ask me. I have in the last class. I have already sent you one of the send you some material from the stress strain diagram. We'll go through this stress strain, and we'll in the next class we'll go for we'll starting the two-dimensional and the three-dimensional stress strain system, or you can say the stress deviators and variance. All will be go through this. So this is all from today from my side. In the next class, we'll start the new chapter. Thank you all. I'll stop sharing here. Thank you all. So one thing is here. Last time there is 10, including me, 10 participants, including me. That means 9. You are 9, joining 9. 9 means Shubhasri Shetty, Priti Sahu, Kirtiranjan Sahu, Anurbha Kuntia, Archana Naik, ଜ୍ୟୋତିରଞ୍ଜନ ପ୍ରଧାନ, ରାକେଶ ପ୍ରଧାନ, Nikon Sahu, Satyajit Nath. So one thing, please do in favor of me. Last class, I think this is the strength. Last class. So please make the attendance of every day's class. Okay.
Sir, Nikon sir is Ekamar Kanan sir.
Nikon Sahu.
Sir, এটা Ekamar Kanan sir.
Ekamar Kanan Sahu ସେ ତ ଲେଖିଛି Nikon Sahu. Okay. ହଉ ଠିକ ଅଛି।
Sir,
ତୁ ଲେଖିଛୁ ନା ତୁ ନିଜେ ଲେଖିଛୁ ନା?
sir ଏଇଟା actually ମୋର laptop ରେ ଏଟା change କରିବା ପାଇଁ time ମିଳିଲାନି ତ change କରିନି।
ହଉ ଠିକ ଅଛି। ତମେ ମାନେ